Hey, welcome to Ones and Zeros. My name's Ben, and today we're going to be taking a bit of a look at a new series that we're starting. So the current series that we're already working on, that's going to continue, but we're starting another series alongside that, looking at some of the more fundamental aspects of programming in C++ in general. Whereas our current tutorial with the STM32 Discovery board is focused more at sort of an intermediate level. Also want to get into producing some videos looking at some of the more fundamental concepts that we're going to be working with in not just our current series, but also some of the other series that are coming up as well. So essentially, we're going to be starting right at the start with this series. Going to be looking at the very basics of kind of how a computer actually functions in the first place. And where variables come into it as far as being able to use those to make a computer do what we want it to do. So what I'll just bring up first up, apologies for that, bit of a hiccup with my microphone there. So going back to what I was saying, essentially we're going to start by looking at a bit of the basics of what a computer does. We'll work our way up to where variables come into it from there. So essentially, if we think of the core parts of a computer, we've got our CPU, or our processing unit. We've got a bunch of input devices. We've got some memory. And we've got some output devices. Excuse my messy handwriting. So with basically how this functions is based on a set of instructions we're providing the computer. It's going to take information either from our input or from our memory, and it's going to perform various calculations or operations on those things, whether we're talking addition, subtraction, multiplication, logic operations, things like that. And then it's going to do something with the results, whether it's putting those into memory or sending those to the output. So as far as input and output, we could be talking about things as far as keyboards and mice, joysticks, stuff like that, or sensors for our inputs. And then for our outputs, we could be talking about anything from an LCD screen through to controlling a servo or an electric motor, sending audio out through a set of speakers, things like that. So if we just have a look at just the memory aspect of a computer, basically the way I like to think of it and find it a bit easier is if we imagine a street, and along that street we have a whole bunch of houses. And much like a street in the real world, each of these houses has a particular address. So in this case, 0, 1, 2, 3, and so on. And each of those houses is basically a box that we can store a number in, because essentially everything we do with computers is based on numbers. So in the case of some of the microcontrollers we'll be looking at, or in the case of the STM32 Discovery board that we've been having a look in the other series, that has half a megabyte of memory, or 512,000 approximately, different locations where we can actually store a value, not including input and output. Now, some values might take up more than one house, so we might have a particular value that might take up 2 houses or 4 houses in order to be able to store the particular values in. Now, typically with most computers you're going to work with these days, you're going to be looking at the smallest house that you're going to be looking at is going to contain 8 binary bits. And although we do some things where we're specifically manipulating bits themselves. Typically, the smallest values we're going to be dealing with is going to be 8 bits. And then we're also likely to be dealing with values that might be 16 bits or 32 bits, which are, of course, multiples of 8. Make sure my screen stays in the right orientation there. So what we're looking at in terms of the particular addresses that we have that point to those different houses is that basically is described as being our address space. Now, not all of the address space is going to be dedicated just to memory. You will have certain addresses, certain houses that may give us access to input devices or output devices, otherwise known as peripherals. So for example, if I switch to this one here, this is actually a display of the memory map for the STM32 Discovery board that we've been looking at in our other series. And on this left-hand column here is the one that kind of describes the particular address space for that device. So we can see down the bottom here, this second block from the bottom where it says 512 megabyte block 1 SRAM. That's the main half a megabyte memory that's sitting inside the chip. And coming out from that, we can actually see that that's broken up into various sections. So our main SRAM that we've been working with is actually that one there, which has 368,000 houses or bytes worth of memory. Now, with that microcontroller and a bunch of most microcontrollers that you'd be working with today, they're typically natively going to be working with values that are 32 bits in size, or that take up 4 of the houses that we were talking about before. And as such, because it uses 32 bits, it's also using those same 32 bits or 4 bytes to describe the particular address that it's putting a value into or retrieving it from, which is represented by these hexadecimal numbers that we've got on the side here. So with our decimal system, we deal with numbers where each column is represented by a value in between 0 and 1. And with binary, we're dealing with something that's a value in between 0 and 1, so only 2 values instead of 10. In this case, with hexadecimal, we're looking at values where each column of the number represents a value between 0 and 15. And that just makes it a bit easier for us to write down long numbers, easier than we could in decimal, and definitely easier than we could using binary. So with the hexadecimal, just so that it makes a little bit more sense, just going on to what I was describing. So if we look at the decimal number system, and we've got 0, 1, 2, and so on, all the way up to 9. Once we get to 9, we end up putting a digit in the next column to give us 10. When we're dealing with binary, we'd be looking at 0, 1, and because we've only got 2 values per column, the next value or 2 would be represented by 1, 0, and then 1, 1, 1, 0, 0, and so on and so forth. In the case of hexadecimal, we're looking at something where we go from 0 and then we go all the way up to 9, much as we do with decimal, but then we need a way to be able to describe the values from 10 through to 15, and in that case, that's where we go with A, B, C, D, E, and F. So in this case here, you'll see, switching back to our memory map, that our numbers here are described, in this case, 1 FFF, FFFF. So that kind of helps that to make a little bit more sense. Now, as far as our input and output devices or our peripherals, you will notice that if we have a look in this block here, this is kind of where all of the addresses are for the particular peripherals in the system. And then we also have some other areas that are reserved for when we're doing things like using external memories with our microcontroller and things like that as well. Now, where variables come into that is in being able to more easily decide where particular numbers are going to be stored within that memory, rather than us actually having to go through and figure all of that out manually, which would be a bit of a pain to have to do for the complexity of different software these days. So if we jump into Visual Studio, we've just got a very simple program set up here, kind of the very basics that you would have for a Windows program. And essentially, we've got just our main function. In here will be all of the code that is going to be executed, so our list of instructions. And then at the end of it, it's going to send a value back to Windows to let it know how it went. In this case, it'd be returning 0. So it's kind of saying everything went okay, there was no errors or anything like that. So where variables come into it is we can explain to the computer that we want to have a value of a particular type or a particular type of number. We want to give it a name which represents the particular location or address or house that it lives in. And to do that, we would firstly describe what type we're going to be working with, and then we would give it a name. So in this case, we're going to go with a uint8t, and we're going to call that A. Now, there'll be various different types that you will come across and that we'll see through this series as well as some of the other videos, and that you may have seen in doing some programming previously as well. So in this case, we're explaining to the computer that we want a value that is 8 bits wide, so one house, and that it is going to be an unsigned integer. So basically, it's a number that only has positive values, so it can't be -1, -2, -3, anything like that. And because it gives us 8 bits, it allows us to store a number in between 0 and 255. Which is a little bit limited, and that's where we will run into other different types as well. So for example, we also have a uint16t and a uint32t, in which case we've got a number that is 16 bits wide, or 2 bytes or 2 houses, going back to our analogy from before. And that allows us to store a value in between 0 and 65,535. So it gives us a wider range of numbers that we can store, but takes up twice the amount of space as the uint8t, because it requires 2 houses to store it. We also have a uint32t, which is 32 bits wide, and of course takes up 4 houses, or 4 bytes in memory, and allows us to store a number in between 0 and I think it's somewhere above 4 billion off the top of my head. Can't remember that one exactly. Now, there's also other particular types of numbers that we can store. For example, we could go with an int8 like that. And in this instance, it still has 8 bits, much like our uint8t. However, this one allows us to store both positive and negative numbers. So we can go with numbers below 0. Now, it's still limited by only having 256 different combinations that it can store. And because some of those need to be able to represent negative numbers, it then means that we can't go as high as 255 in the positive numbers as we can with our uint8t. So it actually has a range of -128 through to +127. And we can also do the same thing in the case of an int16 and an int32. And we might give these guys slightly different names. We want to make sure that all of these have their own individual name, because otherwise things can get a bit confusing. The computer may not be sure exactly what we're trying to get it to do. But these ones all allow us to store a number that has both positive and negative values. So much as our int 8t allows us to store from minus 128 through to positive 127, our int 16 will allow us to store around minus 32,000 to positive 32,000. Minus 32,767 through to positive 32,767. And then, of course, our int 32, which allows us to store a number in between somewhere around minus 2 billion to positive 2 billion. Now, that's kind of the way we work with those. And as mentioned, the particular name that we're giving that is basically just a representation of a particular address on that street where all those houses are, or a particular address in memory where we're actually going to be storing a number. So in this case, we could actually just look at telling the computer that we want to store the number 10 in A and that we want to store the number 20 in B. And we'll get rid of the rest of these guys for the moment, and we might actually create another uint16 and we'll call that C, and we'll say that that is going to be equal to A plus B. And just so that we can have a look at what it's actually doing with that, we can tell it to display that for us. So I'll tell it that we want to have a look at what A is first up. And we'll also get it to show us what B and C are as well, so we can have a bit of a look at those guys. And then we're also just going to pop a thing in there just to stop it from returning straight away at that point. So this is basically just going to get it to pause at that point until we hit a key on the keyboard. So if we run that, it's not actually giving us what I'm looking for there. Let's try that again. Okay, for some reason it doesn't like A. Let's just change that to that one for the moment. I think that's what it might be having a bit of an issue with. That's better. All right, so we can see that what it's done here is put a 10 into A, which we can see there, a 20 into B, which we can see there, and then it's telling us that C, which is equal to A plus B, is equal to 30, which of course is correct. So that then allows us to be able to start to describe to the computer the list of steps that we want it to do, with the variables being almost like the ingredients to the recipe, whereas the instructions of what to do with those are kind of like the steps on how to prepare the particular recipe. Now, there's also other different types that we're going to come across, so not just our uints and our ints. You may come across other things in different software, such as just int, which is typically, depending on the particular system and compiler, is generally going to be a 32-bit signed integer. So as in, it can have both positive and negative numbers. And on this particular computer, if we pop in a uint32, we'll just give this one a name as well for the moment. We'll call this guy H. We can actually see that, change that to an int32, that this one actually refers to type def int32 underscore t. So this is basically saying that this and this are actually identical. Now, if we wanted to go with an unsigned number, you may see something like unsigned int. Now, I particularly prefer to use these uint and int types with the number of bits after them because I find it generally keeps things a little more consistent with describing exactly what values or what type of values we're working with, especially when we're dealing with microcontrollers. So you can see straight away, are we dealing with an unsigned number, so it can only hold positive values? Are we dealing with a signed number or a normal int where it can hold positive and negative numbers? Or are we dealing, what size are we dealing with? Is it 8 bits, 16 bits, or 32 bits? So you'll see those ones being used mostly in the particular code that we look at in our other series. You'll also come across things like chars, so we can tell it that we want to create a variable that is a char. Now, a char and a uint8t are actually very, very similar in the sense that both of these guys are made up of 8 bits typically, and it basically allows us to store a particular value in between 0 and 255. With the char, however, typically that is helping us to describe something as textual, and that's where it comes into us sort of imposing various ideas on the various values that are being stored. So, for example, one of those could be the letter A will equal a particular number. The letter capital X would equal a particular number, and so on and so forth. And if we jump into an ASCII table, we can actually see how that works for most of the text we're going to be dealing with a microcontroller, where, as we can see here, the letter A, capital A, is represented by the number 65, and so on and so forth. We also have numbers representing the lowercase letters, various symbols, numbers that we're going to have in text, and other various control characters and things like that as well. So through linking various ideas up with particular values, that's where things start to become a little bit more powerful, as we do with the char. And that's kind of what starts to turn a computer into not just a fancy calculator, but something that can actually start to represent anything from text to sound to graphics, things like that. Now, other cases where you're going to see in programming particular ideas represented by numbers is when we start to look at Boolean values, which in this case is represented by bool. And let's call him, don't have an F there at the moment, so we'll go with that one. In the situation of a bool, we are still looking at an 8-bit value, much as we are with a uint8t or a char. However, in this case, it's representing either true or false. So in this situation, we're saying that false represents a 0 and true represents anything that is not a 0. So again, using numbers to represent ideas or concepts. And this is something that will come across a bit more when we're helping a computer to figure out what it needs to be doing. So it can look at something and go, okay, if this is true, I need to be doing a particular set of steps. If it's false, I need to be doing a particular other set of steps. You'll also find, as we start to look in some of the future episodes coming up in this series, where we will be using numbers to represent things like particular colors or particular audio, things like that. But this is kind of the most basic concept that you need to get your head around in order to start to understand how programming works, because without variables, basically nothing's going to happen. It also allows us to give particular numbers a bit more context through their names so that we can actually understand what they are as we're working with them. So say if we had a particular location on the LCD screen for a computer or the development board we're working with in the other series, and we wanted to locate a particular pixel on that screen. So in that instance, we've got a 2D grid of pixels. So to represent a particular one, we'd need to give it a value for each of those 2 dimensions, or typically otherwise known as our X or Y value. So in this, say if we were using a uint32t to represent each of those, we could call one LCD underscore X, and we could call another one LCD underscore Y. And we can either pop a value in when we create that, or when we describe to the computer what that is and what type it is and what name we're giving to it. But we can also do that outside of there as well. So say if we wanted that to equal 250, for example. So that's kind of a basic look at what variables are, and coming up in future episodes we'll be looking at how they're actually used. So in this series we're going to be looking at potentially shorter videos than normally been doing, but each of them looking at particular concepts that we kind of need to have a bit of an understanding of to start to get into the more in-depth programming. If you run into any questions or anything like that with the things that we discuss in these videos or any of the videos that we produce, definitely feel free to leave a comment. You can also send an email or jump onto our subreddit and leave a question there if you've got one. More than happy to try and help out. Part of the fun for me with programming comes from starting to have more of an understanding of more different aspects of programming. And I found when I first was getting started quite a long time ago, part of the frustration and the confusion was just not understanding exactly what the computer wanted or how it kind of requires us to work with it in order to get it to do what we need it to do. So hopefully we can shine a bit more light on that sort of thing. On the next episode of this particular series, we're going to have a bit of a look at conditional statements, which are things where we can actually take a value and go, okay, if this particular thing is true, we need to do this. If this particular thing is false, then we need to do this, so that we can actually start to get the computer to do different things depending on what is happening with various different variables. So thank you so much for watching. The details to be able to get in touch with us will come up on this end screen. If you're watching on Twitch, definitely love if you follow the channel. If you're watching on YouTube, definitely would love if you gave us a like, click subscribe. And if you've got any feedback, like I said, feel free to leave a comment, drop us an email, jump onto the subreddit and leave a comment there. And thank you again for watching.